Hey everyone, Mr. Chapter here with the fundamental theorem of calculus, the greatest theorem in all of calculus. I hope you're excited. Objectives today: define a function in terms of an integral and differentiate an integral. This second objective statement is going to be where we start today. So the first part of the fundamental theorem of calculus teaches us how to take the derivative of an integral. So if we let lowercase f be a function and it's continuous, and capital F of x is actually its integral from a to x of f of t dt, remembering that this t is actually known as a dummy variable. It doesn't actually matter because it's about to be replaced. You can take the derivative of capital F by taking the derivative of the integral, which is actually quite simple to do. You just take your upper bound, you plug it into the original function f, and then you multiply by the derivative of x with respect to time, dx dt. And it turns out that's the answer. This only works though if the lower bound is a variable, a constant, and the upper bound is a variable. So the lower bound has to be a constant, the upper bound has to be a variable. All right? The fundamental theorem of calculus part 2, we already covered. It basically tells you how to differentiate, how to take an integral of a function, algebraically, any function. I just wanted to make sure both parts of the fundamental theorem were in a single video, so if you wanted to look back at them later, you could. Okay, big idea time. Defining a function in terms of an integral is a huge idea in our course, and it's not really in our textbook, so this is a big one. Make sure you hone in, pay attention to this concept. Suppose you had a velocity function given. I literally just dropped my stylus. That was awkward. Suppose you had a velocity function given 2t plus 1, an initial condition of x of 1 is 3, and I asked you to find x of 2. Well, in order to do this, back in the day, what you would have done is you would have built position using anti-differentiation, right? So antiderivative of 2t plus 1 would be t squared plus t, and then plus c, of course, because we don't know what the constant is. And then we would use the initial condition. 3 is equal to the position, 1 is equal to the time, and we would say that c is 1. And so therefore we would say position is just t squared plus t plus 1. Oops, I forgot the plus there, plus 1. This right here, this is position. So if I asked you, all right, so what's the position at 2? You would just plug a 2 into this thing and tell me the answer is simply 7. Okay, this is how we used to do things. Well, it turns out there's an additional way to do this that actually proves to be very useful in our course, and that is to build a position function using an integral. Very important concept, and I'll teach you how to do it. So it turns out that when you're trying to build a function using an integral, you're always going to start out with the y value of the initial condition. Okay? That's going to be your constant in this scenario. You're then going to add the integral, and the lower bound of your integral is going to be the x value of the initial condition. Okay? The x value of the initial condition. And the top bound is going to be the variable that you want. So in this case, we're going to want it in terms of t, so that'll be a t. And then you just plug your function in. And I'm running out of space. I'm just going to scooch everything over a little bit. Oops, that's not quite what we wanted to go over a bit. Thank you. And then we'll just do function. And that's really what we're doing here. Okay, let me give you some context. So in this case, the position would actually equal the y value of the initial condition is 3 plus the integral. The x value of the initial condition is 1. That's the beginning of the integral. The variable that we want, well, I want t. I want x of t, so that's going to be a t. And then you basically figure out what the function is, and that's always given to you, 2t plus 1. But I can't use t if I already used t here. So I pick a dummy variable. I'll choose s, because s for chapter. So it would be 2s plus 1 ds. My claim to you all is that these two functions are actually identical. They do the exact same thing. But the one on the right is going to prove to be very useful for us in this section. Let me first prove to you that these actually are the same function. So let's go ahead and prove the initial condition that x of 1 is 3. So it'd be 3 plus the integral from 1 to 1 of 2s plus 1 ds. And we know the integral from one constant to itself is always 0. So the answer is 3. So that worked. Let me further prove it to you by finding x of 2. So x of 2 would be 3 plus the integral from 1 to 2 of 2s plus 1 ds. And I'm going to use the fundamental theorem of calculus part 2 to find the answer to the integral here. So I need to take the antiderivative, and it's just going to be t squared plus t evaluated from 1 to 2, which is 3 plus, I'm going to plug in a 2 first, so it'll be 2 squared plus 2, and then I'll put this in parentheses, minus 1 squared plus 1, kind of like that. And that's going to be 3 plus, let's see, 2 squared is 4, plus 2 is 6, minus 1 squared plus 1 is 2, and then this is just going to be 3 plus 4 is 7. So it worked. This actually gave us the same value. So it turns out that these functions are exactly the same. Okay? Okay, second big topic is a little bit more easier to understand, and that's just how to take the derivative of an integral, and you just use the fundamental theorem of calculus part 1. So it says to take your function, take the upper bound, plug it into the function, so g prime x is going to be sine of 2x multiplied by the derivative of the upper bound, which is just simply 2. So the answer of the derivative is sine 2x times 2. Let me prove it to you. Let me prove it to you using the fundamental theorem of calculus part 2. So suppose I actually just gave you g of x, and I asked you to solve it, okay? All right. Well, if I ask you to solve this, you have to take the antiderivative of sine t, which is negative cosine t. And I'm going to evaluate this. I like to use brackets, not parentheses here. I like to use brackets. Evaluate it from 0 to 2x. So this is going to become negative cosine 2x, and then minus a negative cosine 0. Right? Fundamental theorem of calculus part 2. This just becomes plus. This is negative cosine 2x plus 1. So this is g. So what's g prime? The derivative of g. Well, the derivative of negative cosine 2x is positive sine 2x times the derivative of the inside, which is 2, plus the derivative of 1 is 0. So as you can see, it worked. The derivative of the integral is just using the fundamental theorem of calculus part 1, much faster than using part 2. Another example, g of x is the integral from 0 to x of sine t dt. Find g prime. Top bound goes in. The derivative g prime x is simply sine x times the derivative of x, which is just 1. Answer sine x. Second example, taking the derivative of the integral, so g prime x is going to equal, this goes into t, so it would be the square root of 1 plus sine cubed x times by the derivative of sine x, which is just cosine x, and that's about as glorious as that thing's going to get. All right? So there you have some a little bit of work with the fundamental theorem of calculus part 1 and 2. Both of them. They're both important. I'm going to stop recording now.